Hi everybody, welcome to another video in linear algebra, section 1.9, the matrix of a linear transformation. So what we learned from the previous section is that every linear transformation can be represented in the matrix times the vector. And we define a linear transformation as a transformation that have these properties. Transformation of a sum is the sum of the transformation. Transformation of a scalar multiplication is a scalar times the transformation, and then we have these properties here. Now in this section we focus on how to find the matrix associated to that linear transformation, and after that there will be some nice review of what we have in this chapter. Right, so first, matrix of a linear transformation. Every linear transformation from Rn to Rm is a matrix transformation x to a times x. So a linear transformation can be represented as a matrix transformation. The matrix A can be found by observing what T does to the column of In, and we'll talk about I, which is the identity matrix. For example, if we say the identity matrix of order 3, so we have a 3 by 3 identity matrix. We have 1, 0, 0, 0, 1, 0, 0, 0, 1. This is I3, and I2 will be 1, 0, 0, 1. So 3 by 3, 2 by 2 identity matrix, which we have 1 on the diagonal and 0 everywhere else. And if this is identity matrix, we call this column E1, E2, and E3, or E1 and E2. And E is the column of the identity matrix. Right. Now, the columns of identity matrix of order 2 are 1, 0, and 0, 1, given as E1 and E2. Suppose T is linear transformation from R2 into R3, such that T of E1 is equal to that, and T of E2 is equal to that. So how do we find the transformation of the image of an arbitrary x1 and x2? Right. To do that, we have to write the properties of a linear transformation. That's it. Linear transformation of C U plus D times V is equal to C times T U plus D times T V. So that is the combination of the properties in the linear transformation. So we can split the sum and take the constant outside. Right? We're going to use that properties. Right. Now how do we do that? Now first, we can rewrite x. But the x has two components, x1 and x2, right? Now notice we can write like this. And say, what do we do? Right? Now, think about this. And then we can split that as a sum. A number, we can just add 0 here and let 0 like that. So we can split this in 2, right? Actually, we did this on previous section when we write a solution in the parametric form. Remember section 1.5. Just need to find that real quick. This one though. Remember when we write the solution like this, and we group that into first vector, and then we have that at the second vector, and So similar to what we did there. So we split all of the column for x1 and this column for x2. Right? And then we can factor out the x1. And factor out x2. Right? Now 1, 0, that is E1, and 0, 1, which is E2, which is what? X1 times E1, X2, E2. Right, so X can be written in that form. Now get back to the transformation. Instead of X, we're going to use that transformation of X1, E1 plus X2, E2. And we use the properties of linear transformation. We split that and we write x1 t of E1 plus x2 t of E2. And we do know t of E1 and t of E2, so we can substitute the vectors in x1 x2 right. Now of course in the vector form we can switch to the matrix form already, but take it slow, we have a lot of space here. So we just multiply that x1 inside and multiply x2 inside, and then we combine them. 5x1 minus 3x2 minus 7x1 plus 8x2, 2x1, and then plus 0x2, right? And finally we can put this in the matrix form. The matrix is 5, -3, -7, 8, 2, and 0. And the vector is x1, x2. Alright. By the way, the question only asks us find a formula for the image. So this is the formula for the image. So this is the answer. We already have that. So we transform t of x into that. I just want to write this in the matrix form. So if we want to write this as the matrix form, we say t of x is equal to a matrix times x. So if we write that as a matrix form, it's perfectly fine. So notice that the matrix is found by the transformation of the column of the identity matrix. So it's very simple. We use a lot. We have a lot of example in this section. So if we want to find the matrix corresponding to a linear transformation, what we do is just form a matrix where we do the transformation of all of those columns form the identity matrix. So that's what we have here. Theorem. Let T from Rn to Rm be a linear transformation, then there exists a unit matrix such that the matrix multiplied to a vector will give the linear transformation of x. In fact, A is an m by m matrix whose column is the vector that is the transformation of the columns of the identity matrix. I put all of that into the matrix, and that we have the matrix A, and the matrix A is called the standard matrix for the linear transformation of T. So that is the matrix associated to the linear transformation. We don't have to do much. What we have to do is, what is the transformation of those columns in the identity matrix, and that's what we find the standard matrix A for the dilation transformation T of x equal to 3x for x in R2, right? So that's all we need here is x in R2. So we will look at I2, the identity matrix 2 by 2, 1, 0, 0, 1, and E1 is 1 and 0, and E2 0 and 1. So first column, second column, first column is E1, second column is E2, and all we have to do is just try to find the transformation of E1. Alright, which is 3 times E1, because that is the transformation. 3 times E1, so that gives us 3 and 0. That 3 times E2 is 3 times E2. E2 is 0 and 1, so that gives us 0 and 3. And all we do is just stack the result. So the transformation matrix, the matrix for the transformation is equal to the transformation to the columns of the identity matrix. So in that case, we just have 3, 0, and 0 and 3. Right? So keep in mind that to find the matrix, the standard matrix for the transformation, we just find the transformation to the columns of the identity matrix. And that's what we do in this most of example, this section, we can always do that. Now, let T be R2 to R2 be a transformation, rotate each point in R2 about the origin through an angle phi with counterclockwise rotation for positive angle. Find the standard matrix A for this transformation. Right. So we have the point 1, 0 will be here. The transformation through an angle phi is given by cosine and sine, right? That is the definition. This is the unit circle, so we go from 1, 0 to cosine and sine. Similarly, we go from the point 0, 1 to negative sine and cosine, right? Yeah. This is sine theta, will be the same length, but this is on the left side, so it is negative sine theta, and then this is cosine and that is cosine. So what we see here is the transformation of the 1, 0 is going to be cosine and sine, and T of 0, 1 is negative sine and cosine. The angle is phi, right? I write theta. Sorry. Now what we write is the transformation. Now instead of writing a pawn, I can use the column as a vector, right? So t applied to the vector, instead of write 1 comma 0, I write the vector column 1 0. And instead of negative instead of cosine sine 1 like that, I can write that as a column vector. And then t, the transformation of 0 comma 1, is going to be negative sine and cosine. And the standard matrix is just the transformation of the column of the identity matrix. So we just have cosine and sine, negative sine and cosine. I just keep writing theta instead of phi, sorry. Right, so simple enough. Once again, if we know what transformation of the columns of the identity matrix, we put that in the matrix form, and we have the matrix for the linear transformation. Here we just briefly go through a bunch of different examples. So reflection through the x-axis. So the standard matrix is 1 and negative 1. Why is that? Just going to draw quickly. The pawn 1 0 here will stay the same. But so t applied to the pawn 1 0 is going to be the same. But when it applied to 0 and 1, I'll just write t of e1 and t of e2. This is the reflection, so this is originally this pawn is x equals 0, y equals 1. Apply to this, give us 0 and negative 1. So the standard matrix, we're just going to stack t of e1 next to t of e2. Next to that is t of e2. So we have 1, 0, and 0, negative 1. So very simple. Just find what happened to the columns of the identity matrix that give us a vector, and then put them in a matrix. That is the matrix of linear transformation. So it's very easy. We don't have to memorize any of this. So whatever we do, just find the transformation of those column of the identity matrix, meaning 1 0, 0 1, or in 3 dimension 1 0 0, 0 1 0, 0 0 1. Here we have a bunch of examples. I said we don't need to memorize any of this. Whenever we need to, just find an example. Find what happened to the just find the transformation of the columns of the identity matrix. What happened to 1 0 and 0 1, and then put in the matrix, and that's it. So here we have another example. I said I just put all of that here. Just have some example. Right. We have more example of that in a minute. But now let's study more in theory. Right. Definition. A mapping T Rn to Rm is said to be onto Rm if each B in Rm is the image of at least one x. So kind of difficult to see here, but let's say we have just draw a very simple here. We have Rn transformation Rm superscript onto, meaning that if we have a point in here, there must be a point in Rn associated to it. So every image has a pre-image, right? So if I have the point in Rm, there will be a point in Rn that associated to it. So there will be no point left outside. Yeah. So this is not onto, meaning there's a point in here that doesn't have anything to it. So in that case, it is not onto. Onto meaning that every point in the target will have an arrow pointing shooting to it. Think about this. Every point in the target will have an arrow shooting to it. At least one. This point in the target, but there's nothing going to it. So this is not onto. This is onto. Doesn't matter what, we have a point in here. There must be a point shooting to it. So that is going on to. Next, we have one-to-one. Once again, T is a mapping from Rn to Rm, and if each B in Rm is the image of at most one x, so what do we have here? So again, we still have the same scenario. Go from Rn to Rm. It says here that each B is the image of at most one from here. So if we have one x, there may be an arrow to it. But what we cannot have is two guys shooting at the same target. And we cannot have that. So not one-to-one. We cannot have two guys shooting in the same target, same point on the target. So on two, each point in the target has an arrow pointing to it. This is on two. One-to-one is that every point on the target will get at most one arrow. So there may be a point standing outside, perfectly fine. There will be a point on by itself that doesn't have any arrow pointed to it. That's still okay. But we cannot have two guys shooting in the same point on the target. Right. That's just a definition. Of course, later on they will tie everything together. So that's why this section toward the end of the chapter is very good. It kind of connect all the ideas into one concept. Now, let T be a linear transformation whose standard matrix is that. So we have the standard matrix. Does T map R4 onto R3? So the question is that going to be onto? So in that case, let's just write something like this. A linear transformation, right? Transformation is going to be AX. So we're going to have that matrix. If we want to test the transformation, this is 3 rows, 4 columns. So when we multiply by x, x has to be 4 by 1. So that's how the matrix multiplication work, the middle numbers must be the same, and the outside is going to be whatever it is, it's going to be equal to let's say it's going to be 3 by 1. It is going to be 3 by 1, but let's say that it is going to be y1, y2, and y3, right? Remember, this vector have to be the same dimension as the column of this matrix, right? So let's say the transformation is given like that. Now, does the map, does T map for onto R3? So is that going to be an onto, right? So what do we do here? Actually, just put this in the reduced to echelon form and put it into a metric matrix and do reduced to echelon form. Let's see what do we get from that, right? So for that system, we're going to put in the matrix as follow. A metric matrix will be 1, -4, 8, 1, 0, 2, -1, and 3, 0, 0, 0, 5. It is a metric matrix. We have y1, y2, y3. Right. Let's do reduce to echelon form. Right. Don't worry much about the y1, y2, y3. Just do the operation on the left hand side. Before we do that, let's go back to the definition of onto. Onto means that every point in Rm have an arrow pointing to it. Loosely speaking, every image, every point is an image of a point from Rn. Every point in Rm is an image of a point from Rn. Let me write that down. Every point in Rm is an image of at least, I would just say it's image of point, could be more than one in Rn. So this is the definition of onto, meaning that whatever point we have, this is in Rm, in Rm, and this is Rn. X is in Rn, and the image is in Rm. Now, it said every point in Rm is an image of a point in Rn. Right. Now let's just do the reduced to echelon form, and what can we get from that? Right, 1, -4, 8, 1, 0, 2, -1, 3, 0, 0, 0, and 5. Let's check. Right. As mentioned before, reduced to echelon forms, we can write that in the matrix, in the vector, in the matrix whose entry are fraction, because we just use the row operation, multiply, addition. There's no square root or anything, so we should be able to have fraction. Right. Now, should we do the row operation? There's something applied to this. So we don't know what happened here on the right hand side, so I'm just going to say there's something on that side where that symbol can be any number. So it could be anything. Now let's focus on the solution here. What do we have as the solution? Here we have x1, x2, x3, and x4. We have the pivot here. Right. So let's go back to definition one last time. Every point here, every point in Rm, there will be a point in Rn. There will be a solution. If it is the case, it will be on 2. Now, when we look at this matrix in this state, we say that this one has a solution. May not be unique because they are free variable, but that doesn't matter. The system has solution, or we say the system is consistent. What we can get from the RIF is that the system is consistent. By that we mean it has one solution or infinitely many solutions, but it has solution. One solution or infinitely many solutions. Right. What does that mean? In terms of the question, is this on 2? Now, if I write, elaborate by this, obviously it doesn't matter what y1, y2, y3 is, right? There's always a solution because the reducible echelon matrix come up to that, right? So I will say doesn't matter, or I should say for any point y1, y2, y3, or we say any b, y2, y3 in R3. Now this is onto R3. Any point on R3, there is a solution x such that Tx is equal to b, right? Meaning that doesn't matter what the point y1, y2, y3, doesn't matter what that is, there's always a solution. So that means every point here is an image of a point in R4. Let's be more precise. There is x in R4 such that Tx equal to b. So T is on 2. Yeah. So actually on the in math the on 2 can be written as an adjective. So we just say that. So that means doesn't matter what we have and doesn't matter what the point is in R3, there will be always a point that is associated to it. And that essentially means on 2. Every point on R3 will have a point from R4 associated to it. That's why it is called on 2. That is the definition of on 2. Now, same thing. Is T a one-to-one mapping? So once again, we're going to write this metric matrix again and do the reducible echelon form. So we still have the same thing here. but I'm just going to copy this. So we have the magic matrix. Once again, it doesn't matter what y1, y2, y3 is. The reduced to echelon form, we end up with that with the star can be any number. Alright. Now, what is the definition of one-to-one? Right, one-to-one. A mapping is said to be one-to-one if each B in Rm is the image of at most one X in Rn, meaning that if there's one point on the target, only one arrow can point to it. There cannot be two guys shoot in the same point on the target. We cannot have two guys shoot at the same point on the target. Right, now think about this. One here, and one here. Those are the pivots. We have x3 is a free variable, right? What happens when we have a free variable? By the way, this one once again is consistent. That means it has a solution, but that solution is not unique because of the free variable. So let's just first say the system is consistent, or I should say the system has solution. Because, by the way, why do we know this has a solution? Well, all I can say is that the system has no solution if we have something like that. If we have the pivot on the last column, then that will be no solution. Which we do not have here. We do not have the pivot on the last column. So this guarantees to have a solution. It has a solution. However, because there is a free variable, see, there is a free variable. In this case, the free variable is x3 here. There's no pivot on that column. There's a free variable, meaning that we have infinitely many solutions. Right, that's simple. Of course, we have that already. But in terms of, it's not a one-to-one. Well, think about this. We only have, doesn't matter what y1, y2, y3 is. Doesn't matter what we have for B. There is infinitely many solutions, meaning that there will be a bunch of x. That transform into B. Right? There are a bunch of x transform into B. So we cannot have that. So this one is not onto. It's not one-to-one, sorry. So T is not one-to-one. Because it has, doesn't matter what y1, y2, y3, or doesn't matter what b is, this system always have infinitely many solutions, meaning that there are a bunch of x that corresponding to b, and that is not one-to-one by definition. We can only have, doesn't matter what the point is, there can only one arrow pointing to it. We cannot have two guys shooting the same point on the target. Right. Of course, I put the summaries of this together nicely. But before we go to the theorem and others, just want to point out that we don't even have to do the reduced row echelon form, because what we have here is row echelon form. We do have the leading 0, and so this is in the echelon form. And so we can say that this is an echelon form and there's a pivot every row, so we don't have this scenario. That means we have a solution. And once again, we can say that in the echelon form, this variable is free, so there will be infinitely many solutions. So we don't have to do the reduced row echelon form, because the echelon form is enough to say that this one has solution, but the solution is not unique. Right, we get back to all that. Now, a theorem. Let T be Rn to Rm be a linear transformation, then T is 1 to 1 if and only if the equation of T of x equal to 0 has only trivial solution, meaning that x must be equal to 0. Of course, 0, 0, the 0 vector is the trivial solution. Right. Now, of course, I'm not going to write the complete proof for just one side of the proof, simply as this. Now, suppose that we have that, meaning that there are 2 points corresponding to B, like x1 and x2 both shooting corresponding to B, so this is not 1 to 1, right? But suppose we have that, then let me write this, then we subtract them. Right, and of course T is linear transformation, so we can say the difference of transformation we can write as this. Right, what does it say here? Now, if T is 1 to 1, we cannot have this. Right? If T is 1 to 1, that means x1 has to be equal to x2, because we cannot have different points pointing to the same point on the target. We cannot have, so we cannot have x1 and x2 pointing to the same B. However, if both of them equal to B, then x1 has to be equal to x2. Right? So if it is 1 to 1, then x1 has to be equal to x2. I mean x1 minus x2. x1 has to be equal to x2, which implies x1 subtract x2 equal to a 0 vector. So now, if T is is 1 to 1, then x1 have to be equal to x2. In that case, it's perfectly fine, right? Of course, the same point will point to B. That's perfectly fine. They cannot be different. Now, if they're the same, the difference will be equal to 0 vector. So we have, from this, the homogeneous equation give us, we only have a trivial solution. So we say that t is 1 to 1 if t of x equal to 0 has only trivial solution. So we have that equal to 0 and it has trivial solution. Right, that's nice and all, but what we need to remember in this section, what we need to know is how all of that, or pretty much a lot of different concepts in this chapter are linked together. Let's look at this. When we look at this, we say we know for sure it has a solution, right? Because we do not have a row where the pivot at the last column, the last entry, we do not have the pivot on the last column of the metric matrix. Or if we ignore the last column from the metric matrix, we just focus on the matrix itself. If we have the pivots on every row, if we have the pivot on every row, then what we have is guaranteed to have a solution, right? And if we have the free variable, the solution is not unique. So let's write it out. Right. Let T be Rm to Rm be a linear transformation, and let A be the standard matrix for it. Then T onto, if and only if the columns of A span Rm. It is 1 to 1 if and only if the column of A are linearly independent. So we have the concept of a span and linearly independent. Right. Let me look up for one important theorem that has related to this. This will be in section 1.4. On page 17. Right. Let A be an M by N matrix. The following are equivalent. For each B in Rm, the equation has a solution. So kind of like what we've been dealing with, right? Each P in Rm is a linear combination of the column of A. So that is a linear combination. But more important, the columns of A span Rm. The columns of A span Rm. So exactly what we have. So that's why I said this section at the end, toward the end of the chapter is good. It kind of link a lot of concepts together. So it's a good review. So let me write all the equivalent form here. So the first point we said these are equivalent. Right. T maps Rm onto Rm. Now we focus on the onto. So the column of A span Rm, which is equivalent to in terms of a matrix, we say that the columns of A span Rn, meaning that we have on Rn, on R3 in this case, there is a combination of those columns. The vector is represented by columns. Doesn't matter what we have at the end, there are always a linear combination from the columns here. to give us that. So that is the definition of span. So T maps are, if it is onto, then the column of A span Rm. So in terms of what we look for is that how do we know if the columns of A span Rm? The easiest one is that A has the pivot in every row. So in that case, the equivalent is that A has pivot in every row. Right. Of course, when we say A has a pivot in every row, which is equivalent to practically we just look for, meaning that RREF of A has pivot in every row. So that is the equivalent to onto, meaning doesn't matter what we have, doesn't matter what the image is, there will be a solution. There will be a linear combination of the columns of the matrix that equal to the image. Yeah. And to guarantee that there is a solution, we cannot have one on the last column on the augmented matrix. Notice that when I say the pivot on the last column of the augmented matrix is different than the matrix itself. This is the matrix itself. Augmented matrix, we have one, we come from the last column. So if we only focus on the matrix, we don't have that. If we only focus on the matrix and not the augmented matrix, then we do not have that. In this case, this row does not have a pivot, so potentially that could be no solution, right? If we have one here, doesn't matter. If we have the pivot like that, doesn't matter what we have here or doesn't matter what we have here, it's guaranteed to have a solution, right? The solution may not be unique, but they are guaranteed to be a solution. Or we say the system is consistent. So in terms of the map is onto, we just write that the system is consistent. The columns of A span Rm, or A has the pivot on every row. Practically, that's what we look for. So that's the first part. The second part, what is equivalent to one-to-one? Which will be equivalent to. Now, it is one-to-one, meaning that there must be a unique solution. There must be a unit X for each and every image. Whatever the big image is, there can only be one X that transforms to it, right? So there must be a unique solution. And the onto guarantee to have only a solution, or infinitely many solutions. That's for onto. But for one-to-one, it's the unique solution. Right. So what we look for? So what we look for equivalently is unique solution. Or equivalently, the columns of A are linearly independent. Most importantly, if we want a unique solution, like that, if the solutions are not unique, this is not one-to-one. If we want the unique solution, what we cannot have, a unique solution cannot have free variable in it, so there will be no free variable. Right. So these are the equivalent of the onto, meaning that going to be span, meaning that we have the pivot on every row. One-to-one, there is unique solution and the columns are linearly independent and we cannot have free variable. Right, let's look at the next example. Let the transformation be that. Show that T is one-to-one linear transformation and does T map R2 and R3. And so pretty much ask for if the question is the transformation is one-to-one or the map is onto. Right. So first, let's write T x1, x2 as that. Now let's put that in a vector form. Right, 3 components, just put that in the vector form, and we can split this as a matrix coefficient times the vector x1, x2. So this is the matrix associated to the linear transformation. Is a standard matrix for the transformation. Right, all we need to do is just reduce to echelon form and see what do we have. Or if we write like this, we should just say RREF of the matrix A is equal to three by two. Sorry. Three rows, 2 columns. 3, 1, 5, 7, 1, 3. There's something wrong. So, if we cannot do that, don't worry, there's a trick to that. For some weird reason, actually, if that doesn't work, just artificially add a column of 0 at the end. Don't worry, it will fix it nicely. Right? And it will just ignore the last column. Right? So if we when the calculator cannot do the reduced row echelon form, just artificially add a column to it. So we'll do it, and it will take out the last column. So what do we have here? So what we have here, reduced row echelon form is this. By the way, what do we have for the reduced row echelon form? First, the x1 and x2, right? So corresponding to x1 and x2, we see here there's no free variable. Of course, if we have the geometric matrix, there's something on the right hand side, or in the geometric matrix we can put like the star, 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 and that is the geometric matrix. But we don't need to, just the matrix itself is good enough. Right. So that is the reduced to echelon form of A. What we see is here we have the pivot here and here. So two conclusions from here. First, no free variable. That means there is a unique solution. Or not, it doesn't matter, but just so that it's going to be 1 to 1. Yeah, because depends on the last one, that could be no solution. So unique solution here, unique solution kind of, I put it there because most of the case there's unique solution. But if we, for some special choice here, we might end up being 1 here on the geometric matrix. In that case, there might be no solution. But 1 to 1, if there's no solution, it's still okay. Let me go back to the definition. We did say that we cannot have two guys shoot in the same point on the target, but we perfectly fine having a point that nobody shoots it. Still perfectly fine. So even though when we have no solution, it's still perfectly okay for 1 to 1 by the definition. Yeah, because it said at most could be none, right? So no solution is perfectly fine, but we cannot have infinitely many solutions. So it's not unique. We cannot unique solution is not perfectly fine. I should say no infinitely many solutions. It's better. It's the exact correct statement. So instead what we have is no infinitely many solutions. No solution is perfectly fine. Right. So since we have no free variable, we cannot have infinitely many solutions, which is perfectly fine, and that's why this is 1 to 1. And this one doesn't have the pivot on the last row. No pivot on the last row, which is not, which is implied that this statement is not right, so it is not onto. Right. Once again, if we have the pivot on every row, if we have pivot on every row, that is onto. This case not. If we have a free variable, it is not 1 to 1. In this case, there's no free variable, so it is 1 to 1. Exercise. Show that this is a linear transformation and find the matrix A such that T of x equal to AX. Right. Now, what important in this section is how do we find the matrix for the transformation. And the way we find the matrix is just try to find the transform of the column of the identity matrix. So two important things that we learn in this section is the number one is how to find the matrix of transformation. Pretty much just find the transformation of the columns of the identity matrix. So that's the first thing we learn. The second one is this note here. What do we mean when the linear transformation is onto, and what does mean when it is one-to-one. And the condition, one of them, it depends on the number of free variable, and one of them depends on do we have pivot on every row or not. Right. Now this question we just asked to find the linear transformation, so that it is the linear transformation, and then find the matrix A such that T of x is equal to A times x. Right. So how do we show that it is a linear transformation? Well, by definition. Definition, let me find it. It's on the previous section. Right, linear transformation. This is the transformation. So for linear transformation, we're going to check two things. First, it reserves the addition. And second, scalar multiplication is also reserved. Right, we have to check these two to see if the transformation is linear. All right. So just going to say this is one of the proof thing. So we're going to check the first condition. Right. Now, let's say let u be x1, x2. The reason that we don't write this in the vector form or the matrix form because we don't know if this is the linear transformation or not. So we don't have, we're not sure if there's the matrix represented or not. Right, let u equal to that. So we have what? T of u is equal to T of x1, x2 equal to 2, x2 minus 3, x1, x1 minus 4, x2, 0, and x2. Now let v, instead of x, now let's use y. So T of v equal to T of y1, y2. So instead of x, we just say 2 times y1 minus 3 times y2. Wait. 2 times y2 minus 3 times y1. y1 minus 4 y2. 0 y2. So pretty much just that formula, but instead of x, I use y. Now, let's do T of u plus v. Let's do that later. What we do now is just add these two. So we add T of u and T of v. So we add these two together. Of course, when we add this, we can just add the components, right? So 2x2 minus 3x1 plus 2y2 minus 3y1. Second component, x1 minus 4x2 plus y1 minus 4y2. add in the 0 x2 plus y2. Yeah, we just add the components. So this is t of u plus t of v. I should have more space on this problem. Right. So we have the right hand side of the problem. Now the left hand side. Then t of u plus v equal to t of u plus v. If we add u and v, we will have x1 plus y1, x2 plus y2. Now, we have to look at the transformation here. It says x1, x2, first component, second component. It says 2 times the second component. The second component, x2, y2, x2 plus y2. Subtract 3 times the first component. And then first component, x1, y plus y1. Subtract 4 times second component, x2 plus y2. And then doesn't matter, then 0. And then the second component, x2 plus y2. Now, I've run out of space, but if you look at this t of u plus t of v, and then t of u plus v, these two are the same. If we multiply it out, you see 0, 0, x2, x2 plus y2. These two will be the same. I've run out of space, but just multiply it out. Those two are exactly the same. So that check. And then we do the second check. Is t of cu equal to c of tu? Now, this will be easy. This is u, and this is t of u. So I would say c of t of u equal to. So what I do is I just multiply c to everything here. Multiply c into that. Give us 2c x2 minus 3x1, 3c x1. Yeah, multiply everything, c into everything. cx1 minus 4c x2, 0, and cx2. So that is the right hand side. Now the left hand side, c of u is x1, y1, so c of u is cx1, cx2, and then the transformation of cu equal to cx1, cx2, cx2. And now look at the formula here. 2 times the second component minus 3 times the first component. The first component minus 4 times the second component, and then 0, and then the second component. Now, if you compare these two, they're exactly the same. So this also check because we have these two conditions. This is a linear transformation. Right, so we only do the first part of it. Sorry. To find the matrix actually is very simple. Because we have x1, x2, so only 2 components. So all we need to do is find t. What is the transformation to E1? E1 is transformation of 1 and 0. Alright, now we find the matrix. It says 2 times the second component, 2 times 0, minus 3 times the first component. On the second one, the first component minus 4 times the second component, and then 0, and then the second component is 0. So do that, we have 3 and 1, 0, 0. Right, so that is the transformation applied to 1, 0, or the vector 1, 0. Now, T applied to E2, which is transformation applied to the matrix 0, or the vector 0 and 1. Right, now 2 times the second component, subtract 3 times the first component. The first component, subtract 4 times the second component, and then 0 and second component. Yeah, just replace 0 in for x1 and 1 for x2 in the formulas and put that in the vector or the column, and we have 2, -4, 0 and 1. And finally the matrix, we just stack those two next to each other. Right. So that's how we find the matrix corresponding to the linear transformation. Right. Now the next one is a little more complicated. Let T be the transformation that first perform the horizontal shear map E2 onto E2 minus 0.5 E1 and leave E1 unchanged, and after that reflect the result to x2. Right, so, and of course find the standard matrix. Again, this is from R2 to R2, so the standard matrix is going to be equal to T E1 and then T E2. Yeah, so we just need to figure out what is the transformation of E1 and E2. Of course, E1 is 1, 0, E2 is 0 and 1. Right. Let's just look at the map. Try to draw it here. Right. First, the transformation. The first perform horizontal shear maps E2 onto E2 minus 0.5 E1. So what is that? So E2 minus 0.5 E1. E2 is 0 and 1 minus 0.5. E1, 1 and 0. So what do we have here? Minus 0.5 and 1. So first transformation, it go from E2 map to that, right? E2 map into that. So original E2 is here. It's going to map into negative 0.5 and 1, negative 0.5 and 1. So I will be here negative 0.5 and 1. Right? After that, and then the point E1 we map to E1 unchanged. So just that. Next, there will be a reflection, the result through x2. So this is x1, this is x2. So the point here, instead of that, we move to this side. So the x values, the first component, instead of negative, turn into positive. So this will map into what? 0.5 and 1. Yeah, we flip through x2. And originally, the shear leaves E1 unchanged. So from E1, we're going to have just 1 and 0. But then we have to flip across E2, so it will move to the other side. Instead of 1 and 0, it is negative 1 and 0. So bottom line is the transformation of E1 is equal to 0.5 and 1. That is E2, sorry. T of E1 is negative 1 and 0. T of E2 0.5 and 1. So we stack together. We have the standard matrix for the linear transformation. Right. So once again, if we want to find the linear transformation, just try to find the transformation applied to the E1 and E2 or E3, the columns of the identity matrix. Next, assume T is a linear transformation, right? Linear transformation, so there will be a standard matrix for it. Try to find the standard matrix of T if it rotates about the origin to an angle of negative pi with 4 radians. So again, let's draw a sketch here. Right, since it's rotated, so I better draw a circle of radius 1. Yeah. So in case you want to draw a circle with 2 pens, just hold it very steady like this, and then only rotate the paper. Do not rotate your, do not move your hand. Just keep the hand steady, and only rotate the paper. So the circle here. Right. This unit circle. So this is the point x equal to 1, y equal to 0. Of course, we can write 1, 0, but I did mention this many times. A vector could be a point. It doesn't really matter. A vector has more than one component, so it doesn't matter if we want to write 1, 0 or the vector of 1 and 0 or any different way, as long as we have 1 is the first component and 0 on the second component. Likewise, this point is going to be x equal to 0, y equal to 1. We write that as a vector instead of 0, 1. Right. Now, this is rotate about the origin through negative pi over 4 radian. So we rotate negative 45 degrees. So this point will go, negative pi over 4 radian. So it should be clockwise. So this point we go here, and this point we go here. Yeah, so everything rotate negative pi over 4, so it should be clockwise. So that point goes here and that point goes here. So this point, the coordinate of that, of course, that's 45 degrees or pi over 4. So this is also pi over 4. So in this case, the coordinate here, like I said, we can write x and y, but we just say cosine of pi over 4 and sine of pi over 4. Square root of 2 over 2, square root of 2 over 2. So t transform the point E2 or the point 0, 1 to the point square root of 2 over 2, square root of 2 over 2. Now, transformation of this point compared to this and this point and this point, the first component will be the same, but the y component will be opposite. So this point is going to be cosine of pi over 4, negative sine of pi over 4, which will be square root of 2 over 2, negative square root of 2 over 2. So with that, the transformation of E1 is going to be transformation of 1, 0, which will be square root of 2 over 2, negative square root of 2 over 2. And finally, the matrix is stacking T of E1 and T of E2 in column. And we have square root of 2 over 2, square of 2 over 2, square of 2 over 2, negative square root of 2 over 2. Now if we compare to what we have at the beginning of the section, this is rotation with an angle. And we end up with that. Now, if you substitute negative pi over 4 into it, let I check again. T of E1, so this will be negative. Yeah, this is T of E1 and this is T of E2. Sorry. Now, if we check with what we have on page 37, now if we replace negative pi over 4 into this, into phi, we should have the same thing. I'll let you check that, but it will be consistent to what we have on page 37. Again, of course, you find T of E2, T of E1 to make sure that it don't wait T of E1 first and then T of E2. Right. So that one first and that one second. All right. Next we have this problem. Suppose A is the matrix with 5 pivots. 7 by 5 matrix with 5 pivots. Let T if x equal to AX be a linear transformation. Is T 1 to 1 and is T on 2. Fine. Right, first we know A is 7 by 5. So what is AX? Let's write AX equal to B. Right? A 7 by 5. X is a vector, so it has to be a column. Something by 1. Right. And the middle numbers must match. So X have to be 5 by 1 and B therefore have to be 7 by 1. So that is the dimension. So indeed it goes from R5 to R7. Now is T a 1 to 1 or and is T on 2? Right. The only thing we have information here is that A has 5 pivots. But first, 7. A 7 by 5, meaning that A has how many columns and how many rows? Row by column, always, right? So 7 rows, 5 columns. So we're just going to say T is a 7 row, 5 column. So 1, 2, 3, 4, 5, 6, 7. Right, so 1, 2, 3, 4, 5, 6, 7 rows and 1, 2, 3, 4, 5 columns. Right, this one we have 5 pivots. Of course, the pivot in the echelon form, so it have to align. The only possible way is that we're going to have a pivot on every column, right? Yeah, since there are 5 pivot and there are only 5 columns. We have pivot on every column, meaning there will be no free variable. Because the pivot, we cannot put 2 pivot on a column, right? That's the point of the echelon form. The pivot have to align on the right side of the one above. So in that case, 5 pivot on 5 columns, so there's no free variable. And when there's no free variable, we cannot have infinitely many solutions. Because of that, this is 1 to 1. Next, there are 5 pivots and there are 7 rows. So at least, so there will be 2 rows that have no pivot. And according to the note That is very important in this section. If we has the pivot on every row, that is onto. So this one is not onto, because we do not have pivot on every row. So this is not onto. Right. So if we have free variable, then that is not one-to-one. But since there's no one-to-one, no free variable, so it is one-to-one. We do have a row without a pivot, so that is not onto. If we do not have any row without pivot, if we have pivot on every row, that will be consistent, so there will be a solution, or we say it's onto. But this, we have rows without pivots, so it is not onto. Right. So with that, like I said, in this section, the most important that we need to know is how to find the matrix associated to the linear transformation. The way we do that is find the transformation to the columns of the identity matrix 1 0 0 1. If it is 2, if it is R2, if it is R3, it will be 1 0 0 0 1 0 0 0 1. Yeah. E1, E2, E3. Right, so that's the first thing, how to find the matrix. The second thing is determine if it is onto or one-to-one, and we need to know this, how to determine if a matrix represents a one-to-one transformation, or if it represents an onto transformation. Right, I end section 1.9 here. As always, thank you for watching, and see you in another video in linear algebra.